So I think we kind of reached the critical mass, like 60% or something like that. So yeah, let's start today's workshop. So we still with Dr. Samaphon Tinyanon, and he will lead us through another pane of um, data processing. This one will be spectroscopy. So please take it away.
Thank you, and hello everyone. Have gotten rid of me yet, but this is my last section. So, we are going to look into another really fascinating and very like really foundational method in observational astronomy today, which is spectroscopy. And this is really kind of like the bread and butter of a lot of astronomical science, including supernova science. Spectroscopy is how we figure out what elements are in these dying stars. And people who work on stellar astrophysics, for example, use spectroscopy to figure out what abundances they have in their objects, what the temperatures are, and what kind of velocity these stars have, for instance. So we will today we will look at the physics of spectroscopy, spectral line, all this kind of emissions. We will discuss Doppler effect, and I will go through quickly how spectroscopy is used in astronomy with a few example use cases. There are infinitely many science cases that we use spectroscopy for. So probably we're not going to mention all of them. And then we will quickly look at how basic spectrographs work. How do we disperse light into a rainbow using optical elements like prism or grading? We will talk about important terms that you might encounter in spectroscopy, especially when you look up specification of instruments. So words like resolving power, spectral coverage, and other important aspects of a spectrograph. And we'll discuss a little bit on variations on the theme, what kind of different flavors of spectrographs you can expect that are used in astronomy. So we will look at high resolution spectrograph. How do we make them? Multi-object spectrograph, device that can look at more than one star at a time. And then we will talk about integral field spectrographs, which are these spectrographs that can take a 2D image in which every single pixel has a spectrum. They're pretty cool. And we will conclude with the pane of near-infrared spectroscopy. This is the science I work on, so I can talk about this for days, but let's get started. So spectroscopy, I like to think about it as a like a science of rainbow. This is really figured out likely by Newton in 1672, where he has this prism experiment where he passed light from outside of his room through a narrow slit and pass it through a prism. Then realize that this white light from the sun gets spread out into a color rainbow. And this is I think the only existing drawing of the experimental setup. So I think it's kind of cool. The science with spectroscopy kind of started by Fraunhofer in 1814 when he built a spectrograph, look at the sun, and then realized that you don't get a continuous rainbow. But when you look at it closely enough, there are these lines appearing to be absorbed from the continuous spectrum in the back. So he didn't really understand what caused this, and he wrote it down like this line is let's call it A line, B line, C line, D line, E, F, C, H, and K. So these are now we know as like Fraunhofer lines, and they're still the terminology is still used. Kind of a few years later, Kirchhoff and Bunsen from same Kirchhoff as the circuit law, and also the same Bunsen as the Bunsen burner, and that's how they kind of figured this out. They realized that if you take like a pure element and set it on fire, they emit light in specific lines. So for example, if you put sodium on fire, it glows pretty yellow. And when they look at these glowing light through spectrograph, they realize that it's not just, it's not just a particularly yellow continuous emission, but these emissions really do come in like these specific emission lines. What's more is that they notice that all these different lines kind of like line up perfectly with the absorption lines that Fraunhofer saw in the sun. So if you go back here, it turns out A and B lines are just from the Earth atmosphere. C line is hydrogen. This is hydrogen alpha, the strongest hydrogen line in the optical. D line turns out to be this doublet that come from sodium. And this has caused quite a lot of confusion actually among like astronomers, because it's called sodium D line, but it's also a doublet. So people thought that D stands for doublet, but it's not, because this is from this. And then I forget what E, F, and G are. If you know, let me know. But H and K are calcium. That's also used a lot. So this is the process that they came up with, right? If you have a source of continuous spectrum, say, think about things like light bulb or well, very, very, very hot stars, but most stars have lines. So in this case, you get this continuous rainbow out. But if you put a cloud of gas in front of it with some elements in it, and if you look through this gas, then what you see is this continuous spectrum with absorption lines taken out of it by elements inside this cloud of gas. But if you look at it from the side, then you get to see the light that get absorbed and then re-emitted. And in this case, you observe a bright line spectrum. This is what you would observe when you look at things like a nebula, like Orion Nebula, or like any sort of famous deep space object that you can look at. This is also one I think cool tidbit, is that helium is actually first recognized by observations of the sun. And this is because when people were taking spectra of the sun during a solar eclipse, and this might be interesting for Thai audience, because this is the famous solar eclipse that happened in Thailand. I forget the year. But using this observation, they found a bunch of really strong lines in the optical that don't correspond to any elements known at the time. So, they figure out this must be from a new element. So they call it helium after, helio, the sun. Another interesting kind of similar sort of discovery was from observations of these, I think it was planetary nebulae, and they also saw some lines that don't have, in this case, emission lines that don't have corresponding known element when we observe it on Earth. So, following this observation of the sun, they also named this new element nebulium. And then turned out this is a transition of oxygen that is usually very, very rare. It's called a forbidden line of oxygen. And the reason we don't observe it on Earth is that the density, whenever we get to observe oxygen line, even in like vacuum on Earth, the density is too high for these lines to show up. But in astronomical environments, the conditions are right such that like this so-called forbidden line is the only possible line for gas in these nebulae to cool. So that's why it show up. And it turns out to be a very, very strong line. And especially for supernova science, it's extremely useful to measure mass of oxygen in exploding stars. And this is the reason why we have all these different lines. This is like a 2-minute introduction to quantum mechanics. So we're not going to go into the details, but in brief, atoms have all these different permitted energy levels around it in which their electrons can occupy. And the interesting thing is that we actually have like a analytic solution, like quantum mechanics solution just for hydrogen. Everything else is too complicated. So all the lines and energy levels have to be computed. But for hydrogen, we have it nailed down because it's 1 proton, 1 electron. And these are kind of like all the possible, not all, but the common possible transitions that you can have. Things that transition from like whatever level down to the ground state or n equals 1 is called Lyman series. Most of these lines are in the UV. And of course, the most important one is Lyman alpha, which is at 1216 angstroms. And I know this because my astronomy department has managed to secure that address for their building. So that's pretty cool. And so things that transition to and from level 1 is Lyman. Things that transition between level 2 it's the Balmer series. And this is the first series to be recognized because, of course, they are in the optical. We can see it with our eyes. So hydrogen alpha that we saw earlier is just the transition between levels 2 and 3. Right, yes. Let's see. Yes, and then we have Paschen bracket cone series, and these are all named after some people who make these observations and notice a new pattern before we kind of figure out the root cause of all these fields. If you have time to look it up, the Balmer series also have like really cool kind of like mathematical like equation to predict the wavelength done by I think Balmer is like a school teacher who is just like really loves like this kind of like series problem where we have like 3 numbers and like what's the 4th one. So it was like a completely empirical and like very simple relation. Fascinating. Another really important aspect of spectroscopy and why it's so useful is that we can use it to measure velocity. So I'm sure everyone here has heard of the Doppler effect before. And this is the change in wavelength of light or any wave when you have a source that is moving in relation to the observer. So for the Doppler effect, in cases the velocity is not close to relativistic, then this is the formula for the wavelength shift. Is that the shift in wavelength divided by the rest wavelength is just the velocity divided by speed of light. Once we get close to C, you have to be careful, and there's a full relativistic formula for this. But in astronomy, that is encountered quite often. So you have to be careful. And there are these supernovae called broadline supernovae, where we think there's some kind of like extra energetic explosion happening. And in those cases, we can see V that is as high as 30 or 45,000 kilometers per second. So that is getting quite close to C. So we will see in a little bit how this effect and others can be used to figure things out in astronomical context. So as I said in the beginning, spectroscopy is really foundational to astronomy because it really allows us to figure out what is really going on in these astrophysical objects that, as Dr. Nisha said, you cannot bring into the laboratory. You cannot fly out to and take sample. You cannot fly out to and experience them. So this is really all we get to do is to look, and spectroscopy is one of the most, or like one of the like very basic diagnostic tools that we have. So I would talk about 3 different like really key science cases that have been performed using spectroscopy. And the first one is just simply the chemical composition of the stars. In for generations and generations before, I believe this work was done in the 1800s. We thought that the chemical composition of the sun should not be too different from the chemical composition of Earth, you know, because we think they are formed from all the same kind of like initial materials. So everything inside should be sort of the same. There should not be like a large differences between this. But then a lot of work done by women at Harvard Observatory, and at the time they're called computer because they are not scientists. They're supposed to be, you know, just sitting there and make computation. The thing is, they got to see a lot of data, and of course, they come up with a lot of really, really transformational theory. And one of the work done there during that time is to catalog all the spectra of stars, and then start to try to categorize it into these spectral types and classes. And if you have seen these OB, AFG, KM series of stars that was done there. But really the kind of where this spectroscopic work comes in is by Cecilia Payne, who was a PhD student at not at Harvard, because at the time Harvard also did not allow women to study PhD. So I believe she was at Radcliffe, which is like a female university next to it. And she wrote what has been regarded as like the most brilliant PhD thesis ever written in astronomy. And what she realized is that if you look at these spectra, you see the strength of hydrogen kind of is maximum around A1 and A5 sequence, and then it gets fainter at both higher and lower temperature. And initially people thought that this just means that like A5 or A1 stars just have more hydrogen. But what she figured out is that this is the effect of the ionization state of the hydrogen. The overall amount of hydrogen is kind of the same in all of these different spectral types. But what happened is that at different temperature, the strength of lines change depending on how many hydrogen atoms you have to produce these lines. So at the hot end, for example, all the hydrogens are ionized, so there's nothing to produce lines. She also found that to be able to produce this the hydrogen absorption that is this strong, most of the stars that like most of the materials on the star and in the sun actually has to be hydrogen, which is, you know, when the result came out, it was called like, this is ridiculous. How can you have hydrogen? Like, how can the sun be so different from Earth? And then later on, with more and more confirmation comes in, of course, she is proven right. Another really famous and very foundational work in astronomy that is done by spectroscopy is the discovery of expansion of the universe. And this is done by using the Doppler effect to measure the velocity of different galaxies that we can observe in the night sky. And most of the credit for this work went to Edwin Hubble, kind of deservingly, because he figured out how to measure distances to all these different blobs on the sky. And prior to this work, he also figured out that the Andromeda Nebula that has been imaged, has been known for a long time. It's actually not part of the Milky Way, but it's its own galaxy, very far away. And this work was enabled by the standard candle method that we talked about yesterday. There are these stars called Cepheid variables that whose period of oscillation, that these are variable stars that have regular bumps and wiggles in their light curve. And has been figured out by also one of the female astronomers at Harvard University that this period is the period correlates to the luminosity of the stars. So if you can measure period, which is very easy, you just take a bunch of images, do photometry, and make a time series and make a light curve, can make the period. Once you know the period, you can just look up on a table and get the luminosity. And once you get luminosity, you have the observed flux, you can compute the distance. And this is the method that Hubble used to figure out the distance to Andromeda. And when he has that distance to Andromeda, he also continue and measure distances to all the other nearby galaxies that he can see the Cepheid variable at the time, which are not too many because he's still working off of photographic plate and rather small telescope. So this is the Hubble distances on the x-axis. Very important. However, he did not make spectroscopic observations. These observations came from a different astronomer called Vestal Slifer, who have also, just out of curiosity, he has a spectrograph, he has a big telescope. So he kept taking spectra of all these different, like so-called spiral nebulae on the night sky. And for Andromeda, he found, oh, the lines are shifted to the blue, which means that this galaxy is coming straight at us. So that's one peculiar aspect about the dynamics of the local group. But once he continued making these observations, he found that most of the spiral nebulae are actually going away from us. In fact, I think Andromeda is like one of the very few that has a blue shift. Everything else has a red shift. The whatever absorption emission lines are shifted to the red, meaning that they're moving away from us. So when these two measurements are brought together and plotted onto this now famous Hubble diagram, you can see that there's a clear correlation between the distance and the velocity, meaning that that the universe is expanding, and when you have this situation, things that are closer to you are moving away slower, and things that are like very far from you are moving away very fast. And this is just a linear correlation. If you see a more modern Hubble diagram, you will also realize that it's not a complete fluke, but it's also kind of a fluke because most of the velocities in galaxies that are this nearby are completely governed by the dynamics of the galaxy group and not really in the expansion of the universe flow yet. And this is the reason why his initial measurement of the Hubble constant, which is the constant of this v is this Hubble constant times the distance, like the velocity is this constant times the distance. The initial measurement he made is 400 kilometers per second per megaparsec, but really now we know there's more like 70 with a lot of debate. So the last thing I want to touch on is this radial velocity measurement. This is again the doing of Doppler effect. So if you're paying attention, this was the work that won the Nobel Prize in 2019. And this is a discovery of a really weird, peculiar system called 51 Pegasi. And the planet they found is the size of Jupiter, but it's orbiting closer than the orbit of Mercury. So this is a so-called hot Jupiter because they're so nearby, have very high surface temperature. But the reason why this is kind of like the first type of planet to get discovered around other stars other than the sun is because they're so massive and they're so nearby. So when they orbit around the host star, the stars get tugged around along with it as well, as this animation shows. And when this movement happens, you can see it in spectroscopy. The lines get shifted, blue shifted and red shifted. And you can use this to measure the yes, you can use the size of this effect to measure the mass of the system, and also you can use the period to measure period of the system, and that's how the first exoplanet was discovered. We will notice that the velocity required to make this measurement, if you see on the y-axis here, this is meter per second, and this is about 50 meters per second. And if you recall, for for galaxy measurements, these are 500 kilometers per second, also bad label, and 1,000 kilometers per second. So this is very, very different scales, and we will require very different instruments to make this kind of measurements. So how do we make rainbow and do these measurements? There are kind of two ways to do this. One, we rely on something called Snails Law. And this is really just the kind of like the mathematical way to say that when light tries to get from point, well, in this case, point P to point Q, it will try to take the path that is the quickest, right? Because, you know, just like us, they're very lazy. And it turns out that if you have some kind of material that is not vacuum, the speed of light in those materials slows down. And because of this, the path that it actually takes is essentially the one that kind of balance out the distance that it can travel in the material that that light travels faster, and then kind of balance it out with the distance here where the speed is lower. For instance, if if it try to go straight here, then it will spend too much time in this like material 2 that has lower speed of light. So the equation for this is simply the sine of theta1 over sine of theta2 is n2 over n1 equal to v1 over v2, where v is the speed of light in the different material. The reason why you can use this to spread light is because what is not shown here, n, is actually wavelength dependent. So for different kind of glasses or even water or all kind of materials, this property n, which is known as a refractive index, depends on your wavelength. So different light, so all the white light coming in at the same angle, like this, when it encounters a surface, it will split out. And this is the basis for prism spectroscopy, which is what Newton used, and probably what is kind of like most famous way of doing spectroscopy. Different light, different wavelength bend differently and get dispersed. Now, one kind of fun fact about prism is that with the way that the refractive index depends on wavelength, usually blue light will bend more with prism than red light. So you can always spot a bad science diagram when you have a prism that has more red light bending than blue. Another way that we can do this is to use diffraction grading. And this is actually kind of like the preferred way that we do it in astronomy. And the reason is because prism is still used in a lot of instruments, but there are sort of two problems with it. One, you cannot get very high resolution because the amount of spreading you get just depends on the property of the material, and there are so many materials we can choose from. Another problem with doing spectroscopy with prism, well, not really a problem, but kind of an annoyance, is that the dependence of the refractive index on the wavelength is non-linear. So the final spectrum you get on your focal plane will not have a regular spacing of wavelength. Both of those problems are kind of solved by using diffraction grading. So who here have seen this like diagram before, when light passes through two holes and then interfere? So essentially, this diffraction grading works by limiting the path that light can take to the point that light going through it will create this interfering pattern on the focal plane. And the important equation for diffraction grading is this so-called grading equation, which is just that d sine theta is m lambda, and this is just a path difference between the two light paths going through two consecutive groups. And this is a condition where these two paths will constructively interfere at this point P on the screen. You will also see that for fixed D distance between groups, which is always the case because we manufacture this grading, and if m is some integer, then different wavelength lambda will end up at different angle theta. And this is the basis of how diffraction grading works. This is true for all orders except for when m is 0. When m equals 0, you don't get any grading. So this is a picture of a diffraction grading in action. This is the reflective type. So some incident light comes in, reflects off of this diffraction grading, the reflective type. And then you see the m equals 0 order. Sometimes people just call it the 0th order. Does not have any dispersion at all. And then you get m equals 1. And then some light also goes to the negative order, -1. And then you have some light going to m equals 2, 3, 4. You might be asking, okay, so we get so many different rainbows from here. Which one do we use? And that's the one real key issue with diffraction grading, is that you always waste light into orders that you don't care about. There's a way to optimize this. There's something, a technique called blazing, which this is getting a little bit technical, but what it is that you can build a group into your grading in such a way that you maximize reflection into the direction of the order that you care about. And usually for astronomical spectrograph, this is blazed into the first order to try to maximize the transmission into the m equals 1 order, and try to minimize light into other orders, especially the 0th order, which doesn't do anything for us. There are also some, you can also notice that with the same grading, if you use m equals 1, then you get this amount of dispersion. But if you use the m equals 2, the light spread out a lot more. So some spectrographs also use this to their advantage and say, if you need more resolution, you can switch to using the 2nd order, but you will suffer like lower transmission and whatever problem. Another effect that this can have is that once you get to higher and higher orders, they actually overlap. And if you try to use a spectrograph at orders 3 and 4, for example, they will almost completely overlap. We'll talk about how to deal with that in a little bit, because there's also one kind of spectrograph that really uses this back to its advantage. So in the basic spectrograph, what we have is that you get light coming in from the sky, and then it will encounter the primary, either mirror or lens. Here it's just drawn as lens. just to be simple. The light focuses onto a focal point, focal plane. If you want to do imaging, this is where you put your CCD. But for spectroscopy, we will pass this light through a narrow slit. We'll see in a bit why. And then there's a second piece of optics called a collimator. And what this does is that it takes this crossing beam of light that is now kind of converging, and then it collimates it back to a parallel beam. And this is because whatever spectral dispersion optics we use is best operating in this collimated beam. If you put a grading into this diverging or converging beam, it can work, but the computation becomes more difficult, and also the results are not as good. So usually you collimate the light, bring it back to this parallel beam before you pass it through a prism or a grating. And then after that, the light is still collimated, so you have to bring it back to a focus. And this is done with another piece of optics, usually referred to as a camera. So and this can in a lot of well, not a lot, but in some spectrograph, actually you can just use a commercially available like camera lens to do this. It's really the same thing. You just take a picture of the rainbow, and then you put it onto a detector and read it out. So in a way, the data we get are really similar to photometric data in a technical sense. Of course, the content on it is very different, and we will learn how to deal with that in the section after the break. And this is why slit is very important. So the top figure here is from LRS. I'm stealing your figure. So this is the spectrograph that we are working on at NARIT, called the low resolution spectrograph, very creatively, and it's going up to the 2.4 meter telescope. On the top picture, this is object called NGC 2392. This is the planetary nebula, one of those things that have really, really strong emission line. On top, this is a spectrum you get from this object if you don't have any slit on it. So you can think of it as this whole 2D image smeared out in wavelength direction. And you can see they're kind of like a two really bright copies of this image here and here. Any guess which line this one is? Red. So this is hydrogen. Yeah, this is H alpha. And this kind of like pink, blue, purplish. This is the nebulium line. This is the complex that has H beta and also all these forbidden oxygen lines. So, okay, cool. This is cool and all, but if I pick this point and ask, how bright is this nebula at this specific wavelength? You don't know, because there's this confusion of is this like 4,800 angstrom from this part, or is this like 4,500 angstrom from that part, right? There's this spatial confusion. And because of that, we in spectroscopy, we often try to isolate this spatial direction by putting down a slit that get rid of all the light in one spatial direction and only allow one the orthogonal direction pass. And when you do that, instead of all this mess, you get this clear, clean line of light. So here, say if you put the slit here right past the core, then you know that this line is whatever wavelength of this part, and that line is whatever wavelength of the same part. Now, if we want, the trade-off here is that if you want information on that part, then you have to move your telescope and move your slit. So this is not ideal, and we will talk about how to deal with that in a little bit. Now, slitless spectroscopy is still really, really important, and the reason is because you have a huge image. If you don't need a high resolution, you can just put the prism or a grating in front of your optics and just get a bunch of spectra of everything in your field of view. And that is actually how the Hubble Space Telescope does spectroscopy for a lot of the instruments. So this is from my data from with really bizarre supernova. Come talk to me if you're interested. But it turns out this is the most sensitive way we can do infrared spectroscopy before James Webb was launched. So we got some time on HST to make this observation, and you can see that there's no slit involved. You just take the image, put the grating down, and smear everything out. Quick thing to point out is that this is a supernova, and you can see that the spectrum is not like very continuous. It's very bumpy, and it's a bunch of lines here. That's why it was fun. And it corresponds to like kind of So let's talk about these different terms that I promised. So one is the resolving power. It's kind of like the number that everyone that gets thrown around a lot when we talk spectroscopy. This resolving power is the wavelength divided by the wavelength resolution. And in some cases, it's more useful to tell you that like the actual wavelength resolution, like what the smallest wavelength difference you can resolve with your spectrograph. But you can figure that out from the resolving power number. And also usually it's reported like this because the resolving power remains more or less constant for prism spectroscopy. So this is again kind of a historical thing. When people talk about low resolution spectroscopy, including LRS that we are building, we refer to a resolution of about 1,000. And because this is lambda over delta lambda. So if you remember from earlier, the Doppler effect formula is very similar. So R can actually tell you immediately what the velocity resolution you have with your spectrograph. And it's just the speed of light divided by R. Yeah. Medium resolution is usually like 10,000, and high resolution is closer to 100,000. But this is just all like rough number. To some people, 1,000 is medium resolution, and low is like 100. But that's a matter of semantics. It's not very important. So a lot of factors affect this resolving power. More like fundamental is the grading spacing, and this is almost always reported when you look up the specification of a spectrograph. It will tell you how many lines per millimeter, for example, is on the grading, and from that number you can gauge like things with more lines per millimeter will have higher resolution. And a lot of spectrographs will also allow you to pick which grading you want to use. And they will have like this kind of like a turret wheel that can bring different gradings into the optical path. Another kind of like thing, property that you cannot change is the pixel scale of your detector. If your instrumentationalist did a good job, then the pixel scale should be very well matched with the real resolution of the spectrograph. So you don't oversample the spectrum, which means you have too many pixels for one spectral element. And when you do that, you just spread things out onto too many pixels and get more read noise, which you don't want. Or you also don't undersample it, which means the whole spectral element. So if you have a really narrow emission line, it doesn't fall onto like 2 or 3 pixels, with just like less than the area of 1 pixel. When that happens, it's also bad because you're not getting all of the information that your optics can provide. And the last factor is the slit size, because if you remember from the figure, if you increase the width of the slit, then more the information in the spectral direction gets more confused, and because of that, your like resolution you can rely on decrease. The usual trade-off here is that if you remember the figure with order 1 and order 2, to get higher resolution, you have to spread out the light more, right? And when you do this, if your detector is still the same size, then the kind of like the range of wavelength that you can detect is smaller. We'll see in a bit how to deal with that. Do that. I'll move to this side. Can people on that side see the screen or on Zoom? Okay, so if you can see this screen, there are empty seats on this side, so please move. We have 10 minutes. But we are wrapping it up. I'm gonna go through this different common type of astronomical spectrograph and how we use all these different properties, weird and wonderful properties of gratings to make astronomical observations. The most basic type is what we saw before. This is a long, so-called a long slit spectrograph. So you just have a narrow long slit. Usually the width is around one arc second, but you need to pick the size that is appropriate for the seeing that you have at your site. And most spectrographs will also have a option for you to pick which size you want. But that's pretty much it. You get the slit, the light comes through it, go through prism or grading, and then hit the detector. And this is relatively easy to build. So, and that's the reason why this is one of the most common type of spectrograph that we have. Most telescope has one. You can see in this direction, this is the source, the bright thing, the bright line in the middle, and that's just the point source that gets spread out into the so-called spectral direction. And then in the spatial direction, if you happen to have another star landing on the same slit, then you can get a second trace showing up. But in this case, we don't. It's just one source. So these vertical lines are actually emission lines from the night sky. I should have looked it up what these lines are, but I didn't. And this is on the blue side of the spectrograph. So this is around a wavelength of 300 to like 500 nanometers. In the infrared, or even in the red optical, there are a lot of these sky lines, and these are from the OH bond between in water essentially that vibrates and emit. Those are really annoying. Yeah, and this is the data from the CASP spectrograph at the 3-meter chain telescope at Lick. I mentioned these high orders overlap, and this can actually be used in this type of spectrograph called Echelle spectrograph. And this is used to make high resolution observation with still very wide wavelength coverage. And the way it works is that all these different lines that you see, all these different kind of like horizontal lines, these are all different orders of the grading. And usually These are very high order, so something like 65 and 66, 67, 68, and these things can have like 20 or 30 orders. And you can see that in spectral direction, they're all overlapping, right? They're all at the same place. So to prevent confusion, because if you don't do anything to it, if you just pass light through Spectral Grading and just image it, you get one line with like all the orders on top of each other. So what you can do in this case is that you can put a prism or a different diffraction grading. We use a prism, but you disperse light in the perpendicular direction. So the grading disperse light in this direction, and you put in a prism to disperse the same light in that direction. And when you do that, all the different orders get separated into this kind of like neat and nice image on your detector. And this is a typical data coming from this so-called shell spectrograph. It's really cool. Like you can have resolution of like 80,000, 100,000 with the wavelength coverage still from say 300 to 800 nanometers. So a lot of like all of the high resolution measurements, things like exoplanet discovery are all done by this type of spectrograph. And this is from the Levy spectrograph from the APF telescope, also at LIC. And this is a very similar telescope to the one we have here in Thailand. There's also a subset of spectrograph. We will see data from one in a little bit. That is called echelet. So instead of having like these, like 20, 30 orders, it will just have usually like 4 or 5. And this design is more commonly used in the optical, in the near infrared. We can also have a multi-opted spectrograph that allows light from different sources to be observed at the same time. Because of course, if you have like a cluster of stars or more commonly galaxies, and this is something that Dr. Nisha works on a lot, so you can go talk to her about that. There's also a design that can allow all these different points or all these different sources to get observed at the same time. And that's because if you remember this long slit image, usually the full image is much bigger than this. And most of the detector is not being used because it's only one source in it, right? So in the multi-optic design, you can design an area like here. I don't know if you can see clearly on the screen, but there are all these different boxes. And for this particular spectrograph, the way it works is that, weeks before your observation, you have to send in your mask design to the observatory, and then they will go out and take a plate of stainless steel and cut it in the places that correspond to your source on the sky. And then on the night of your observation, they shove it into the spectrograph and then only allow light from those different sources to come through. This is one of the possible design for multi-optic spectrograph. There's also this one really cool design also at Keck with 46 metal bars that can be reconfigured on sky to create the mask pattern that you need. So that's quite cool. The downside is that it takes like 10 minutes to do. So when you're on sky doing observations, 10 minutes is a long time. And the last design I want to talk about is this integral field unit, or IFU, sometimes called IFS, or integral field spectrograph. This is something we are also working on here at NARIT. You can talk to Dr. Bright about this. And the promise of IFU is that, well, you don't need to pick anything ahead of time. Let's get the spectrum of everything on this 2D plane. There are several ways to do this. Yeah, I just say use magic, but really it's like a combination of either image slicers or a bunch of fiber optics to get spectrum of every single point on this 2D plane. Usually this is done using some sort of like a focal plane unit that does all the magic with slicing up the light, and then it passes on to a more traditional spectrograph. And usually on the spectrograph, what you see is like just a bunch of spectra that will have to be reduced and processed and then put back into this so-called like a cube, like data representation. If you're interested, come talk to me after. I can show you more pictures of this IFU design. Usually the trade-off of this IFU is that, you can do this over a huge area on the sky because you can only cram so much information onto your small detector. And yeah, that's a common trade-off. I think the biggest field of view IFU with like a sufficient resolution on sky is called MUSE. This is the instrument at the VLT telescope in Chile, and it can get data over a field of view 1 by 1 arc minute. And it does so by a complete brute force. There's, I don't remember, maybe like 10 spectrographs attached to it. So like if you look up image of MUSE, it's just like the ginormous instrument. So we'll conclude with talking about the plane of near-infrared spectroscopy. So this is the islet design I promised you about. There's only 1, 2, 3, 4, 5, 6. There are a few more down here, orders, and not 20 or 25. And the reason is because the near-infrared waveband usually goes from about like 1 to 2.5 microns. And this is a much broader range of wavelength compared to the optical. So you need kind of like more detector real estate to do it. But so let's see. Let's look at all the awful things that this have. So one, many more skylines compared to the optical. All these vertical lines, these are all from the night sky, and you can see that this is really bright compared to our faint little object. This is like some supernova. There's also a bunch of water absorption bands. There are like this huge strong band here. There's another really strong band here. This arrow is misleading actually because that one particular absorption is actually from carbon dioxide in our atmosphere. You also have really strong thermal background once you get close to 2.5 micron, and this is just the thermal background from your telescope and from the air. The detector that we use in the near infrared are not as good as in the optical. So the darker end is higher. There's a lot more hot pixels and noises. And then the last thing, which is kind of particular to this specific spectrograph, are all these point sources that show up. The first time I used this spectrograph, I was really confused because, I didn't think that it has an imaging mode. And I was like, what are all these different stars? So I asked the telescope operator, and they're like, oh, no, those are not stars. What those are is that in the infrared, because this spectrograph works from about 0.7 to 5 micron, the kind of materials they need to build the lenses are very, very limited. And at the time that they were manufacturing this spectrograph, which was in like the early 2000s, the only material they could use had thorium in it. Of course, thorium is radioactive, and it will spit out alpha particles into the detector. So all of these points are helium ions that are getting detected by our CCD. So that's just some personal event. You can come talk to me later if you want to know more about infrared spectroscopy. It's annoying, but you get really good insight into a lot of astronomical optics. That's why we keep doing it. But let me close by going through quickly the steps of spectral reduction that we will see in the notebook. So first step, we still have to do all the basic reduction. We have to do flat. We have to do bias. If we are in the infrared, sometimes we have to do dark, but these days it's getting better. Thankfully, this has already been done for you in the notebook, so you don't have to deal with the basic reduction again. So once you have the image, you have to find out where the trace is. So you have to define, which like region on the detector you have to like your source is located, and you have to extract the light. So that's called spectral extraction. You have to subtract background, similar to when you do photometry. The sheet will tell you how to do background subtraction. And then you have to figure out where on the detector corresponds to what wavelength. And usually we do this by either in the infrared. It's helpful because there's so many sky lines. You can actually use those lines to figure out this so-called wavelength solution. In the optical, usually we use some gas lamp with known line. Normally it's argon, mercury, cadmium, I think. Argon. There's so many, there's so many of these lamp lines you can use. So usually there's a observation of those lamps called arc lamp that you can use for wavelength calibration, and that is what we will use for our notebook. And lastly, I don't think we will do this for this section, but you also have to flux calibrate your spectra, again, similar to how when you do photometry. And for spectroscopy, usually we do this by observing a star with a very, very well-known spectra. This is a very short list of like really few stars, and people who do optical spectroscopy all the time will have like their favorite calibration stars, which is kind of like ridiculous. But you can ask them like what standard star they use, and they can tell you from the top of their of their memory, which is funny. One closing caution about flux calibration in spectroscopy is that you can never and you should never trust them. Usually the absolute level is always wrong by a factor of a few, but the shape should be relatively correct. And that's why you almost always, if you need an absolute flux spectrum, you also need photometry at the same time. And the reason is because you never observe standard star and your target at the same time. It's also different part of the sky. And because when you're using slit, the transmission of light through that slit depends strongly on how well the source gets centered on the slit. Usually you don't know it very well. And that's the reason why you have to be careful with spectral flux calibration. But that is it for me this morning. Let's go eat some snacks, get caffeinated, and get ready for the next notebook session.